Before we jump into talking about what was on the exam, I want to go over this sheet that I've just posted onto Canvas, which is something of a guide to muscle function and muscle properties. And I'm realizing that having something like this on the exam as something analogous to an equation sheet might have been very helpful for you. So I've made this, and you can add this to your notes for the course. So what this has is, number one, a table up here that shows you the different abbreviations and the definitions of some of the things that we run into, like this F naught, the maximum isometric force, the optimal fiber length, the maximum shortening velocity, the physiological cross-sectional area, and the specific tension of muscle. And then there is an interpretation for each of these over here that tells you what is roughly the maximum isometric force. How do you interpret that? And then down here, I have the 4 important characteristic curves of muscles, and then, well, 3 curves for muscle and then 1 for tendon. This curve down here for tendon is something that we actually saw in Unit 2. The idea being that when you stretch a tendon past its slack length, then it starts to produce force, and you have this kind of nonlinear toe region and then a linear portion up here. And that's just showing that stretching out a tendon produces passive force. Down here, we have the same thing for muscle, and I drew an analogy between the passive force production of muscle that happens no matter whether the muscle is activated or not, and that because of the titin proteins and sarcomeres, if you stretch out a muscle beyond a certain length, that length actually happens to be the optimal fiber length, then it starts passively producing force, just like a rubber band. Up on the top left, we have the active force length curve, and this tells you how much force can a muscle produce as a function of what its fiber length is. And remember, when you stretch out a muscle, the fibers get longer because the sarcomere ends are coming apart. And when you shorten a muscle, the fibers or the sarcomeres get squished together. And so there's this optimal point right here where the overlap between actin and myosin is just right, where the muscle force production is maximized. And whatever length of the muscle fiber that is, we call that the optimal fiber length, or this L naught. And again, that's right up here if you forget what that symbol means in the table. And whatever force is produced, whatever maximum amount of force that a particular muscle can produce, when you get the fiber length just right, that is what we call the maximum isometric force of the muscle. And it occurs at the optimal fiber length by definition. So there's this narrow little region right here where you can produce the maximum amount of force. And then if the fibers are too long or if the fibers are too short, the ability to produce force goes down. And we usually express this as a fraction of whatever the maximum force production capability of the muscle is. So if a muscle can produce at its optimal fiber length 100 pounds down, say here, at 1.5 times the optimal fiber length, it can only produce, well, it looks like about 0.45. So 0.45 times 100 is 45 pounds of force. And likewise for, say, over here, right, at whatever this fiber length is, maybe 0.7. This is also expressed, by the way, as a fraction of the optimal fiber length. So if we found that the optimal fiber length for a particular muscle was 10 centimeters, 0.7 of that would be 7 centimeters. So at that length, it would be, looks like just over 0.8. So that would be, if the maximum isometric force was 100 pounds, it'd be about 80 pounds or so. Then lastly, over here, we have this force velocity curve. So as a reminder, all of this is assuming that the velocity of the muscle is 0. Once we start considering if the muscle is contracting concentrically like this or eccentrically like this, then its force production capabilities change as a function of the velocity as well as a function of what the length is. So this point right here is the same as this point right here. When the velocity of a muscle is 0, that means you're doing an isometric contraction. And so you're going to be producing whatever that maximum isometric force is. And then there's this interesting property of muscles where when they're contracting eccentrically, so when the muscle is trying to contract but it's getting longer because the whatever external force it is greater than the force the muscle is producing, that actually enhances the force production capability of the muscle. So using our previous example of a muscle whose maximum isometric force was, say, 100 pounds, if you are maybe at an eccentric contraction right here, it looks like you'd actually be able to produce 140 pounds, 1.4 times 100, at this fiber velocity. Now, this is expressed as a fraction of this special point right here, the maximum shortening velocity. And the interpretation of that is, as your muscle is contracting concentrically, as that concentric speed increases, so say you're doing bicep curls or bench press, and you're trying to do it faster and faster and faster, there's some speed at which beyond that, you cannot produce any force at all. And we just call that the maximum shortening velocity of muscle. So hopefully you will find this sheet useful. I think it contains all of the, or almost all of the essential pieces of information that you'll need to put together to understand the function of a particular muscle in a particular movement, such as the problem set 3, the analysis of the squat.